All right, 6.4, we're going to be spending some time looking at rectangles. In 6.2 and 6.3, we talked about parallelograms and how to prove if a quadrilateral is a parallelogram. Now we're going to recognize and apply the properties of rectangles and then determine whether the parallelograms are rectangles. So in doing that, just looking over the 7 properties of a parallelogram, all of these have to hold true in order for a quadrilateral to be a parallelogram. Well, some of these here, if you think about what you already know about a rectangle, you should be able to say opposite sides are going to be congruent to each other, opposite angles are going to be congruent, and we can check off a bunch more here. And what's going to end up happening is actually all 7 of these properties hold true for a rectangle. So what that means is that every single rectangle that's out there is a parallelogram. And so every rectangle is going to follow the 7 properties that we have here for parallelograms. Now on top of that, rectangles have a few specific properties that are only applied to rectangles and not to every parallelogram. And those are the fact that you must have 4 90-degree angles to be a rectangle. And you also need to have diagonals that are congruent to each other. Now, what we know about parallelograms is diagonals are not always congruent to each other. Our diagonals here, they're going to share the same midpoint. They're going to bisect each other. And so we've got, it's creating 2 congruent triangles. We have all those properties. But also being added to that is the fact that our diagonals are congruent to each other. We have to have 4 90-degree angles, and that creates a rectangle for us. So going ahead and showing you an example of how we can solve rectangles using some algebra here. Trying to solve for x and y. I'm going to start with solving for y. I'm given that BD is 2y plus 10 and AC is 3y minus 30. Well, what I'm referring to here are the 2 diagonals. And one thing that we just talked about is how the diagonals are congruent to each other. So BD is going to equal AC. So that means that 2y plus 10, it has to equal 3y minus 30. If I solve, subtract the 2y from both sides, 10 is equal to y minus 30. Add 30 to both sides. And here we end up with y is equal to 40. And so that's because the diagonals are congruent to each other. Then if I'm trying to solve for x, now with those diagonals, we know that diagonals are congruent. We know from our properties of a parallelogram that a rectangle has opposite sides that are parallel to each other. So even though BC and AD are congruent to each other, they're also parallel to each other. Well, with that being said, now this diagonal is acting like a transversal line. And so now you have these 2 angles, x squared plus 1 and 3x minus or plus 11. These 2 angles, going back to what we did, I think in chapter 4 it was, they are alternate interior angles. And if we remember about alternate interior angles, they're always going to be congruent. So we can go ahead and say that x squared plus 1 is going to equal 3x plus 11. Solving, one thing I notice right now is that I have an x squared, so we're going to be working with a quadratic. And so now we have to take everything and get it equal to being 0 so I can try and factor this out. So I'm going to subtract a 3x from both sides, and I'm also going to subtract 11 from both sides, leaving me with x squared minus 3x minus 10 is equal to 0. Factoring this out, looking for 2 numbers that are going to multiply together to get negative 10 and add together to get negative 3. X minus 5 and x plus 2. And now x minus 5 equals 0, x plus 2 equals 0. So x is going to equal positive 5 and x is going to equal negative 2. So I have 2 solutions for our value of x, 1 solution for y. So we'll be using those properties both for a parallelogram and for a rectangle when you're working with rectangles. And now we want to go ahead and see, well, how do you prove that you have a rectangle and not just any quadrilateral or not any parallelogram? So here I have a quadrilateral of ABCD, and we're going to look at how can we prove that this is a rectangle. So when we talked about proving if a quadrilateral is a parallelogram, we worked with really like 3 different options. One of the options showing that the opposite sides are parallel, so you could use the slope 4 times. Another way is showing that opposite sides are congruent using the distance formula 4 times. Another way is to show that the diagonals share a common midpoint, and then that gives us the midpoint formula twice. So from everything that's going on here, that's to prove if this is a parallelogram. But what we want to do here is we want to prove that it is a rectangle. And to prove that it's a rectangle, we have 2 properties that we can work with. The fact that there's 4 90-degree angles, or the fact that diagonals are congruent. Now, 4 90-degree angles, what we can do here is proving that there's 90-degree angles. We're talking about lines being perpendicular to each other. And so that is going to relate to that first one here, working with opposite sides being parallel. If you use your slope formula, what that's going to do is tell you if you have 2 lines that are perpendicular or not. You're trying to look for that opposite of reciprocal for the slope. So by showing that you have 4 90-degree angles, that's enough for us to say that we have a rectangle. What we have to be careful with is showing that the diagonals are congruent to each other. Because originally you're going to think, okay, I just have to use the distance formula 2 times. Unfortunately, we have to go a little further than that, because a parallel or a rectangle is not the only quadrilateral that has diagonals that are congruent to each other. A trapezoid also does, and so a trapezoid is not considered a parallelogram at all, but a rectangle is. So if we want to show that the diagonals are congruent to each other, we are going to have to first show that it's a parallelogram to then be able to show that the diagonals are congruent to each other. So to show you a couple examples of what we can do is probably the 2 most popular ones are going to be using the slope formula. So I can use the slope formula 4 times, and by doing that I'm doing the slope of AB, BC, CD, and AD. Now, A, B, and BC are next to each other, so I'm going to look at those 2 slopes. The fact that those 2 slopes are opposite reciprocals of each other mean that they are perpendicular to each other. So that means we're creating a 90-degree angle with AB and BC. There's our 90 degrees. If I look at the next 2, BC and DC, those 2 right there are also perpendicular to each other. So I've got BC and DC, so we're creating another 90-degree angle. If I take a look at DC and AD, here we have 2 opposite reciprocals of each other, making it perpendicular. So we have a third perpendicular line. And then finally, if I take a look at our AB and our AD, there are opposite reciprocals as well, so they're perpendicular. So the slope formula here tells me that I have a parallelogram because opposite slopes are the same, and it's also showing me that I have a rectangle because there's 4 90-degree angles. Another idea here is the fact that you can show that your diagonals are congruent to each other using the distance formula twice. But then what we have to do is we have to do one more piece of information to prove that this is a parallelogram and a rectangle versus a trapezoid. And so here, when you're looking at this, an easy way to prove that it's a parallelogram is to show that the diagonals share a common midpoint. So using the midpoint formula for our diagonals, they share a common midpoint. They both have the same distance, so therefore we have a rectangle. And that's probably the hardest part about now trying to put all of this together. We started dealing with our parallelograms, and now we're going to try and be more specific, working with rectangles, and we're going to talk about squares and rhombus later this week. So hopefully now you can see what the additional two properties are for a rectangle, and then seeing how we're going to now prove that a parallelogram is a rectangle.